Alright, I'm going to apologize in advance for this video. It's from section 4.3, it's problem number 8. And although the concepts aren't that bad, the algebra and the computation is kind of nasty, so this is probably going to be a longer video. So what we're looking at is a function of x, which is equal to x minus 9 over x squared minus 25, and we're analyzing this between 0 and 5, not including 5. And so where we're looking at this graph is we're including 0, and then we're going all the way to 5, but not including 5. A good first step, especially if you have a graphing calculator or Desmos free graphing calculator on your computer, is to graph it right away. And this will kind of help us as we're taking our derivatives and our second derivatives. These are all things, for example, we could do this without pre-graphing it, but there's a lot more computation, a lot more math, and it's going to take a lot more time. So it's good to utilize our resources. When we look at this graph, we'll notice that at x equals 0, we have a local maxima, because it's higher than everything that's around it. Then we'll notice that we have a local minima right about there. That's where the graph starts to go up again. And then, it goes all the way up to infinity, so there's not really another local maxima. So, first step to finding the critical points, which could be local maxima or minima, or absolute maxima or minima, is to take the derivative of f with respect to x. So df dx, I'm going to use the quotient rule, so it's low x squared minus 25, low d high. D high is the derivative of x minus 9, which is just 1, so I won't write it down, minus high, which is x minus 9, d low, which is the derivative of x squared minus 25, which is 2x, all over low squared, so all over x squared minus 25 quantity squared. And so right there we did low d high minus high d low all over low squared. That's the quotient rule. This is what we're left with. Let's go ahead and simplify it. So I'm going to multiply my 2x in. So I'm going to end up with x squared minus 25 minus 2x squared minus 18x all over x squared minus 25 squared. Now we can distribute this minus sign into those two terms, and that's going to give us minus 2x squared plus 18x. And then over here we have nothing left to distribute, so we can get rid of our parentheses. X squared minus 2x squared is negative x squared plus 18x. And then we have minus 25x. Or plus 18x. So we have negative x squared from canceling these two out, plus 18x from this one, and then minus 25x from this one, all over x squared minus 25 squared. And this is our derivative, but remember with critical points, at the local maxima and minima, our slope is going to be 0, because if we have a minima here, our tangent line, or the slope of our, or the value of our derivative, the slope of our tangent line, is always going to be 0 whenever we're at a maxima or a minima. And so we're going to set this equal to 0 to find our critical points. And then it's going to be a little bit of algebra. The great thing about this denominator is we don't really have to deal with it. We can multiply it over to this side, and the 0 eliminates it, which is nice. So what we end up with then is 0 equals minus x squared plus 18x minus 25. And what I did when I was solving this problem the first time through was I multiplied everything by minus 1, because I usually don't like a minus sign in front of my first term. unless I'm not going to be factoring it. So I attempted to factor, multiplied everything by minus 1, so my minus x squared became positive x squared, my positive 18x became minus 18x, my negative 25x became positive 25x, and I realized pretty quickly I wasn't going to be able to factor this one, and this is the point in the problem where I realized that this was really going to be a pain. So we're going to use a quadratic formula. And so let's see how much I can fit on the board here. Our a is 1, our b is minus 18, our c is plus 25. So negative b is going to be 18, plus or minus the square root of b squared, that's minus 18 squared. 18 squared, that's 324, minus 4ac, so 4 times a, which is 1, times c, which is 25. That's subtracting 100, all over 2a. And a is 1, so we just end up with 2. These are going to be the x values of our critical points calculated using when derivative equals 0. So those aren't going to be all the critical points, but those are going to be the ones that can be found using the derivative. And so 324 minus 100 is a positive 224, which is good. That's a positive number, so there's no complex numbers. So now this is 224. And now we can simplify this by dividing both by 2. So 18 divided by 2 is 9, plus or minus square root of 224 divided by 2. Square root of 224 divided 2. What I like to do here is I want to get my 2 under the root. So 2 is equal to the square root of 4. So I can substitute square root of 4 for 2. And then another rule of divided roots or multiplied roots is that we can actually put them under the same root. So 224 divided by 4 comes out nice and even to square root 56. So 9 plus or minus square root of 56. Now I want you to remember that this graph f of x, it's not entirely continuous, but it does have values all the way from negative infinity to positive infinity. We are only curious about this graph when it is including 0, above 0, or less than 5. So we want to check and see if any of these x values are within that range from 0 to 5. And so let's do some decimals. Square root of 56 is 7.48 roughly. If I add that to 9, I'm out in the 16 range, 16.48 roughly. I don't want this value because it's above 5. And then what if I take 9 minus the square root of 56? That's going to give me 1.517 roughly. And that is a value that I do want because it lies in the domain that I'm interested in. So I'm going to keep 9 minus root 56. So one of my critical points, x, is going to equal 9 minus root 56. Alright, so now that we're there, now we're going to take the second derivative. I'm going to go ahead and label this my d f dx. And the interesting thing about the second derivative is that it actually will tell you the concavity of the graph. So in other words, the first derivative tells you the slope at any given point. The second derivative tells you how the slope is changing. Now, for example, if the slope is increasing, so we're going from a low slope to a high slope, that change in slope is associated with concavity up. So in other words, our cave is facing up, because as we go from left to right, the slope's increasing. Now, if we go from left to right and the slope is decreasing, then that would be concavity down. And so, essentially, if we calculate, so let's take the second derivative here. what to get rid of. Let's get rid of this. I don't need this anymore. I've got my one critical value I calculated from that, which is 9 minus square root 56. So d2f, the second derivative of f with respect to x, so d2f divided by dx squared is going to, I'm going to use the quotient rule again, which is low, d high, so x squared minus 25 squared, that's low d high. D high is negative 2x plus 18. So that's low d high minus high, which is this whole expression up here, minus x squared plus 18x minus 25. D low, this one's going to be a little tricky. We've got to do the chain rule and the power rule. So we bring down the 2 to the front of x squared minus 25, and then we multiply it by the derivative of the inner function, which is 2x. I'm sorry, these are multiplied together, and we're dividing everything by low squared. That's x squared minus 25 to the fourth now. Alright, so now we have this function that's going to tell us whether we're concavity up or concavity down. Now, if the change of the slope is positive, if the slope is getting more positive as the graph goes from left to right, that's going to be concavity up, and that's going to be a positive value. If the slope of the graph is changing, so the rate of change of the rate of change is going down, then that's going to be a concavity down. And so let's start by checking this point right here, and go ahead and plug it in here. And honestly, that is just going to be a whole lot of math. So I'm going to have you take my word for it, because if you graph this, you'll notice that this value right here is x equals 9 minus root 56, and it is indeed a local minima. Now, if it's a local minima, would you expect it to be concavity up or concavity down? And this is where things get weird. If, in fact, you have a local minima, your concavity will be positive. And it kind of makes sense, because if the rate of change of the slope is positive, then it's getting bigger and bigger slope, right? Which, if you have a bigger and bigger slope, if you're going up, that means that you are down at the time. And if you're going down, that means you're up at the time. So it's just counterintuitive. If your second derivative spits out a positive number, when you plug in your x value, that means it's a local minima. And if you plug in your value and you get a negative, so you plug in your critical point and you get a negative second derivative with respect to x, then you're in fact looking at a maxima. So just think about it as reverse. Through your second derivative, if you get a negative, you're looking at a maxima point, and if you get a positive, you're looking at a minima point, if you're plugging in your true critical points. So anyhow, at this point, I just really didn't want to do that math. It's a lot of plugging in numbers, and I just don't have enough board space for it. So what we're going to look at next is over here on the graph that we graphed on our calculators or on Desmos. You'll notice that this critical point we solved for is a minima, and that this is a maxima right here. And in fact, just by looking at the graph, we can tell that x equals 0 is a maxima. The reason why it didn't show up when we set our derivative equal to 0 is because, remember, one of the requirements of a limit that gives you a derivative is that you have to have a left-handed and a right-handed limit. So one thing that setting the derivative equals to 0 tends to leave out is the left and right endpoint of your domain. So let's find our maxima. That's part A. So our maxima we decided was at x equals 0, so one of our ordered pairs is 0 for x, and when we plug in 0 for x, we get minus 9 over minus 25, which gives us 9 25ths. So this is one of our maxima. And then the other one is, let me check here. Okay, so the only maxima value is this value. And you may be tempted to say that one of the maxima is at when x equals 5, y equals infinity. And the thing that disqualifies that from being a maxima is that we're not including 5 in our domain. We're going to 5, but we're not including 5. And therefore that means that x equals 5 will not be in our domain. So we won't include it as a maxima. So that's part A. Now we're going to look for our minima. And we know of only one. It's the critical point we solved for. And so our minima is when we plug in x as 9 minus root 56. And then once you plug that into your original function and simplify, which once again I've already done it once, I don't feel like doing it again, you end up with something like this. You end up with minus root 56 divided by 112 minus 18 root 56. And this is just as far as I simplified it. I'm sure you could simplify it further, but my math lab was happy with this. So this is the minima. Remember, we solved for this point as a critical point. We looked on our graph to confirm it was a minima. However, if we wanted to confirm it was a minima using our second derivative, we would plug in the value for x of 9 minus root 56. And if it gave us a positive value, that would mean it was a minima. And so this is our only minima, this is our only maximum within the domain we've been given. The last question is there, the last two is there an absolute maximum? And the answer is no, because you'll notice that there's no standalone point that is higher than everything else on this graph. And so we don't have an absolute maxima. For example, well, do we have an absolute minimum? Yes, we do, because within this domain, there is a local minima right here at x equals 9 minus root 56 that is absolutely lower than every other point on the graph. It's lower than any other point on the graph. And so, looking here, we can tell we do have an absolute minima. We do not have an absolute maxima. So we don't have an absolute maxima. We do have an absolute minima, and we've already solved for it. So we'll just plug that in again. I'm going to try to find a problem that's easier to use the second derivative method to show concavity, because that's an important tool. But thank God we live in the era of graphing calculators, because you would have to do that every single one of these problems. You'd have to take a second derivative and plug in the values, the critical points. So I hope this was helpful. Thanks for your patience, and I'll see you next video.